Ooh. All right, so let's jump into, give me a second, whiteboard. Let's jump into 8.2. So I gave you guys two reading problems. 8.2 is about some properties of relations. So we talked about relations in 8.1. In 8.2, we want to look at some patterns, some properties we see with relations, and this is where we're going to get to some proofs. So we want to either give a counterexample when the relations don't have that property, or we want to prove it using an official proof when they do. So let's start out with 2 and just kind of talk through both what these patterns are. And then, I think 2 is more about counterexamples, 9 is more about proofs. And then we'll go on and do a couple more problems just to give you some more variety of contexts, just different types of relations for you to think through these patterns on. Good. So go to. So 2 gives you a relation. So notice the way that they gave you the relation is kind of our stock basic way where we just give you the ordered pairs. And there are 3 properties that we want to talk about. So what I want to do first is let's just kind of not just list these properties. So you saw this in the section, you read through the section. But let's really talk through what kind of the pattern, the idea, what it means. So the first property that we're going to look at for all these relations is called the reflexive property. And notice reflexive comes from the word reflect. So that's actually helps me remember what this property is about. So where the reflexive property is about looking at your relation and figuring out, is every element related to itself? Does it look at itself in the mirror? Does it see its own reflection? So this is reflexive. So R is reflexive if and only if. All X and, well, okay, I don't want to, never mind, give me a second. I don't want to write it. You guys have the official way of writing it in the book. I want to kind of pare that down to something that just makes a little more immediate sense. So give me a second, let me so if we got a relation R, so let's say R goes from let's say X to X. When we talk about relations having these 3 properties, reflexive, symmetric, and transitive, these actually, you can only do this on relations where the domain and codomain are the same. Because you'll see we want 2 things to be related to each other, but they have to come from the same set. So our domain and codomain has to match. So on these types of relations, it's reflexive if and only if X is related to X for all X. So if you look at, so it's reflexive if and only if every element in your domain is related to itself. So it has to be related to itself. So think about, for instance, that last relation that we looked at on the previous video on 8.1. That last relation, all the numbers, I think it was 2 through 8, were related to themselves because they all divided to themselves. So that's a good example of that relation is reflexive. Every single what do you call it? Yeah, every single X, every single input that I'm looking at is related to itself. The metric, so the second property, and I think of, for me, so again, reflexive, I think of reflect. So it has to see itself in the mirror. Symmetric, when things are symmetric, they're sort of balanced on both sides. So the idea is there is there's an even relation on both sides. So I'm gonna have two different elements. So here, what I'm gonna do is I'm gonna pick two different elements, but as long as one is related to the other, then I see the reverse. I see symmetry. So this is not an if and only if. This is if, well, it's an if and only, but what we want to focus on here is if X is related to Y. So if I pick two different elements there, if X is related to Y, then Y is related to X. So I see symmetry there. Now this one's symmetric, unlike reflexive. So reflexive, I'm saying, like I said, if you think back to that last example we did in 8.1, everything has to relate to itself. Here, I'm not saying that everything has to be symmetric. I'm saying if there's a situation where I see X is related to Y, then for the relation to be reflexive, I have to see the reverse, but only for those particular ones where X is related to Y. And then there's a final pattern called the transitive pattern. You've probably seen the transitive property for, again, somewhere deep in your memory, deep in some algebra book, maybe a calculus book. But the transitive property ends up coming up a lot, not only in mathematics, but I'd say a lot of logical situations. So really quick, the transitive property usually is something like this. Basically, if X maybe gives me Y and Y gives me Z, then I can say that X has to give me Z. And this makes sense because if X gives me Y, but also Y gives me Z, so I have to have these two things first. Well, that means Z is just a stand-in for Y, so X would have to give me Z. Or you could think about it more like function composition or like a process that X gives me Y, that Y turns to a Z, so X has to give me Z as well. So this is the way you've seen transitive property before, maybe in a college algebra book. They would probably just use equal signs instead of those arrows. I tend to think of these things, I mean, equals is fine, and we'll kind of see in the next section why equals, what do I call it? Yeah, the equals relation is helpful for stuff like this. But I tend to think of things as process because you kind of see as you get into higher mathematics that even operations, they're a process. You're taking two things, doing some action to them, and producing a third thing. So yeah, things are equal, but there's really a process going on, and it's in the process that you have the patterns. Anyways, so the transitive property. So we're going to say something similar here. We're going to say if, and we need two things, just like, so if X is related to Y and Y is related to Z, whatever that relationship is, I don't care. I don't even care if I know what the relationship is. Like we're going to see in this first example, as long as I got ordered pairs, I know that things are related to each other. So if X is related to Y and Y is related to Z, then the same logic applies. Then that means Z is essentially a stand-in for Y. Or that means, or no, again, another way to think of it is X produces Y, Y produces Z, then X has to be related or produce Z. Now, again, notice with the transitive property, unlike, again, the reflexive property. So the reflexive property is the only one that says this has to happen for all the things, all the elements of my set. The rest of these are just, if you see a situation, then you better see the result. And if you don't see the result, it's not. So again, with symmetric, if I see X is related to Y, then I better see Y is related to X. And if I don't, then that relation is not symmetric. And it again only has to happen once. So like any other counterexample, like any other pattern or property, you just need to see it fail once, and then it doesn't apply to everything. So if also for the transitive gives me more requirements. So again, I'm not saying everything should look transitive. I'm saying if I see X is related to Y and I also have to see Y is related to Z, then I better see X is related to Z. And if I don't see that, then this relation is not transitive. But if I do see that every time, again, not for every element, but if I see that if every time X is related to Y and Y is related to Z, then X is related to Z, then bam, I've got a transitive relation. And if every time I see X is related to Y, then Y is related to X, then bam, I got a symmetric relation. But I only need one failure for it not to be those. All right, so let's look at the relation in two. Again, kind of what I want to what we're going to see today is we're just basically going to look at these relations and just try to identify, try to analyze, is the relation reflexive, symmetric, and transitive. And there's all sorts of variations. So these properties are not like properties that maybe should always happen or should always come with each other, or if you see one, you should get the other. There are all kinds of relations that have all sorts of combinations. There are relations with none of these. There are relations with one of these. There are relations with two of these. There's no real, again, there's no real pattern to, oh, a relation should have such and such property. We're just gonna look at them and see what they have. And 8.3 will start to make a little sense of there are certain types of relations that tend to have, that not just tend to have, that actually have all three of these, what do you call it? All three of these properties. So if you have a relation with all three of these properties, we give it a special name, like as far as a type of relation. And I don't wanna reveal the cool surprise, but it relates to something, a relationship that we already know. Anyways, relations relates to something. Sorry. All right, good. So let's look at two. So two, they give me this relation. So zero is related to zero. Zero is related to one. Oh no. Yeah. One is related to one. One is related to two. Two is related to two. And two is related to three. All right, so this is my relation. And we're gonna go through, so what she wants you to do is basically, what does she say here? Give a counterexample in each case in which relation doesn't satisfy one of the properties. So here, when you have a relation that has a finite amount of, ordered pairs, that's finite, that's not a for all, then we can sort of, if it does fit the property, we can sort of identify it, and if it doesn't, then we can see the counterexample. You don't have to do what I'm about to do, but I will say that if you can see it from this list, that's great. Like go with that. But one of the things that's really helpful in doing a problem like this, where you have these ordered pairs and it's a finite amount, is the directed graph that we just did in 8.1. With the directed graph, you can pretty immediately see which of these properties hold and which don't. So what I'm going to do is I'm going to make a directed graph of this. Based off of the order pairs I see here, it looks like my domain and codomain is the numbers 0 through 3, the integers 0 through 3. So I'm going to put a 0 here. I'm going to put a 1 here. Let's put a 2 here, and let's put a 3 here. So I'm going to go ahead and make a directed graph. And actually, let me move this over so we'll have more room to kind of write the answers here. Zero, 1, 2. It's a baseball diamond. Great. Home, first, second, and third base, but sort of chiral, sort of the other handed approach. Anyway, sorry. So what do you call it? Like I said, 0 through 3, we have 0 goes to 0, so this goes back to itself. We have 0 goes to 1. And then we have 1 goes to 1, so 1 goes back to itself. And then we have 1 goes to 2. And then we have 2 goes to 2. And 2 goes to 3. So this is the directed graph of that relation. And like I said, you don't have to do this, but this I think will help you much easier identify which of these properties we have. So let's start with the reflexive property. So the first question is, so what she's trying to get you to do is you're literally going to list each three property and just basically, does it have that property? And if it does, she doesn't say here, but basically, well, yeah, I guess on these, if it does, you just say yes, but if it's no, you give a counterexample. So basically, you should always justify your answer. But essentially, this picture justifies it in a finite case like this. Give me a second. I just don't want us to get too confused for stuff later in this section. Well, no, I think what I'll do is if it's a yes, we will try to justify it. So we'll kind of give some description. I do think that that's her intention here. She just didn't write it. So never mind what I just said. We will actually try to justify it. That's what she's gonna do this whole section is, does it have the transit, you're gonna do all three properties. Does it have the property? Yes or no? If it's a yes, prove it or show it. If it's a no, give her a counterexample. So same thing we've been doing for all of our proofs. So let's look at the reflexive property. Reflexive property means for every X in my domain, it's related to itself. So what do you guys see here? Is every element related to itself? Good, no. Clearly 3 is not related to itself. So it is not reflexive, and there's your counterexample. You just got to write that. So for reflexive, we're going to say no. 3 is not related to 3. Good. That's our counterexample. So now symmetric. Symmetric, again, what I'm saying is I'm not saying everything has to be related to something else. I'm just saying when I see X is related to Y, then I should see Y is related to X. So for instance, by the way, X and Y don't necessarily have to be different, but it's usually easier to consider different different elements. So for instance, 0 is related to 1. So 0 is related to 1. If this was symmetric, then I should automatically see 1 related to 0. I should see an arrow coming back. And notice that I don't. And not just there. I mean, 1 is related to 2. If it was symmetric, then I should see 2 related to 1, and I don't. And etc. 2 is related to 3, but I don't see 3 is related to 2. So that means this is not symmetric. And any one of those cases is a perfect counterexample. You just need to give one. So symmetric. That's a no. 0 is related to 1, but 1 is not related to 0. So that's my counterexample. Again, for symmetric, it should be symmetry. If one is related to another, then you should automatically have the arrow back. Now let's look at transitive. So like I said, transitive even has more requirements. So in transitive, again, I'm not saying everything should be related to another and a third. I'm saying when I see X is related to Y, and also then that Y is related to another element, Z, then I should see X is related to Z. So another way to think about this instead of X, Y's, and Z's is if I have a first element related to a second element, so first related to second and second related to third, then I should see first go to third. Baseball reference. So for instance, here, notice that we have 0 is related to 1, and then also 1 is related to 2. So for this to be transitive, when I see this, first goes to second, second goes to third, then I should see first goes to third. I should see 0 goes to 2. So if 0 is related to 1 and 1 is related to 2, for this to be transitive, I should see 0 goes to 2. And notice here I don't. So again, as long as one of these doesn't work, this is not transitive. So for transitive, the answer is no. And again, you want to give sort of that full explanation. 0 is related to 1. 1 is related to 2. but 0 is not related to 2. First related to second, second to third, but in this case, the first doesn't go to the third. And again, I just need this to fail once. So it fails plenty of other times actually in this diagram, but we just need to show one of them. Good, so this is an example of a relation that's neither reflexive nor symmetric nor transitive. It has none of those properties. That. The rest of these are great examples. All right, so but that'll get you guys kind of set up for a problem that mimics that. So this relation is none of those three. Let's look at some more relations. Let's see if we can get some relations that at least have some of these what do you call it? Properties, these patterns. So this one, we have to do the slow erase on this, but we'll go to the next reading question, number 9. And let me just erase this part. Now, maybe we'll have to erase it more. And then we're gonna erase all of this. All right, so number 9. And in number 9, they give us a relation. So this is more relation. They give it to us in words or in equations because we can't list out everything in the relation. We can't list out every ordered pair. So they have to give us a description, and then our mind can use that description to kind of imagine all the possible ordered pairs that this relation contains. So this is saying R is the greater than or equal to relation. So R is actually going to go from, in this case, the real numbers to the real numbers. And the description of this relation, so X is greater than, so like I said, they're calling this the greater than or equal. So this is a more algebraic relation just because it has to do with some arithmetic and algebra that you've seen before. So this is the greater than or equal to relation. So X is greater than or equal to Y if and only if. So what we're trying to do here is the things that are related to each other. So X is related to Y if X is greater than or equal to Y, which sounds redundant. And it kind of is. But this is my relation. So I'm saying I pair things based on the fact that the first number is greater than or equal to the second number. So, like I said, here, my relation by nature, I can't list all these ordered pairs out. So in order to, we're gonna try to figure out, is this reflexive, symmetric, transitive? On these, if any of these are true, so if they're false, you give a counterexample. But if they are true, then you're gonna have to actually prove it using a proof. And so that's kind of what I want to dig into. So actually, yeah, let me bring all of these words back here. All right, so the first question is it reflexive? Which means, is every element related to itself? So in terms of our relation, is every element greater than or equal to itself? So you kind of want to think through that. Is every real number, every number greater than or equal to itself? And what would you guys say? And at least it's probably obvious to you. It's definitely, I mean, a number is not greater than itself, but it's definitely equal to itself. And greater than or equal, that's an or, it includes both possibilities. So it's either, as long as it's one or the other, it fits. So every number is equal to itself. So every number is greater than or equal to itself. So In this case, it is reflexive, and so you want to prove it. Um, so to prove it, I'm gonna do a direct proof. Um, I'm gonna do a suppose, and then I'm gonna show that it fits the condition that I want, which is for every number I choose, x is greater than or equal to itself. So I'm gonna start out, suppose x is a real number. Then surely this is so x is greater than or equal to x. Again, I'm using this symbol as a stand-in for the relation, because that's what the relation is, it's greater than or equal. And this is to the reader by basic arithmetic and what we understand about greater than or equal, this is obviously true. This is gonna be one of the few proofs that you do where you basically don't need any tricky argument that builds from you introduce some construction and you do some algebraic manipulation or something like that. It's just pretty obvious both to you and the reader that x is definitely greater than or equal to itself because it's equal to itself. I mean, that's actually, again, for this whole class, we're assuming, so basic arithmetic and algebra that we know, we're assuming that as, as knowledge, both for ourselves and for the reader. Good. So this is reflexive. Every element is equal to itself, so it's greater than or equal to itself. Now let's think about symmetric. So for symmetric, what I'm doing is I'm thinking about a situation where one number, and so again, our relation is greater than or equal to, one number is greater than or equal to another number. And if I have that situation, I want to be able to reverse it around. I want to be able to say, so if first is greater than or equal to second, I want to be able to say the second is greater than or equal to first. And is that true? Does that make sense? Good. Notice that, that doesn't make any sense. At least that doesn't make any sense from what we understand from greater than or equal. So again, intuition and sense tells us in this case that it's false. But then since it's false, we need an actual counterexample. So we need, tell me one number in a second where the first is greater than or equal to the second, and then let's show that the reverse doesn't work. So give me some numbers. Good. So again, this is gonna be no. We could say something like 5 is greater than or equal to 3, surely, but 3 is not greater than or equal to 5. Notice the format of that is exactly like the counterexamples that I was doing for problem 2. So tricking me, that's why I pricked problem 2 before we did problem 9. But that's all you need to do. You just need to give me a counterexample. So again, a counterexample means you are choosing an example. You're choosing two numbers that make the relation work one way, but in this case, it's not going to work the opposite way. So this relation greater than or equals is reflexive, but it's not symmetric. Now let's think about transitive. So transitive, like I keep on saying, you kind of have more requirements there. So in terms of this problem, we're going to think of three different numbers where first is greater than or equal to second, and second is greater than or equal to third. And then we want to test, does that always mean that the first is greater than or equal to the third? What would you guys say? Second, actually. Oh, do they actually do cases on this one, or can we just shortcut it? see here. Okay, good. Yeah, they don't do the cases here. Okay. All right, but kind of thinking through the numbers, does this seem to work? So hopefully your intuition is kind of telling you it does seem to work, so if 5 is greater than or equal to 3, and then 3 is greater than or equal to 1, then definitely 5 is greater than or equal to 1. So the fact that the first two, the first is greater than or equal to second, and the second is greater than or equal to third, at least intuitively seems to force the first one to be greater than or equal to the third, because the third can't be bigger than the second, and the second is not bigger than the first. That's at least equal to the first, right? So that seems to work. And in fact, not only does that work, but we can prove that just using, again, basic arithmetic that we know with our greater than or equal to sign. So this is a yes. And we're going to start out then as a proof. We're going to suppose. So we're going to suppose everything in the if part of this transitive definition. So this is another reason why I wrote these definitions up there. If you notice, I'm usually always tricky about when we get some new definition. I like to try to write it up in some way because, like I've kept emphasizing, if we need to go prove things, especially if it's a direct proof, then once you write it out in if-then form, you've got the structure you prove. You know where you're starting, you know where you're going. So we are going to suppose everything in the if part of this, we're just going to retranslate it with this greater than or equal sign. So suppose X, Y, and Z are real numbers. So again, first I need to identify that they're real numbers, that we're playing in the same sandbox, the same domain as this relation. And X is greater than or equal to Y, and Y is greater than or equal to Z. Good. So I'm supposing everything about the if part of this statement. Then, once we know these two, we know clearly from what we know from arithmetic and greater than or equal, then that again, X has to be greater than or equal to Z. Yeah. So X has to be greater than or equal to Z. And that's it. If I can show the then part, I've got the proof. So hopefully for you guys, when you do this homework, some of these proofs are going to be shorter than a lot of the proofs we've gotten used to. But part of this is because it's just about context, really, the context that you're working in. But especially if you're working in these sort of algebraic arithmetic contexts, you can assume a lot of that arithmetic. And we already have a transitive property for greater than or equal. We already know that if X is greater than or equal to Y and Y is greater than or equal to Z, that forces X to be greater than or equal to Z. You learned that a while ago, maybe in 6th grade, something like that. Or at least that's probably the first time you saw it. So that arithmetic, I know, so I can write it down, and there we go. We got the proof. Good. So the greater than or equal to relation is reflexive and transitive, but not symmetric. So those were our two lead-ins, the reading questions. Let's do two more questions, or two more of the questions like this. So like I said, all the questions in this section are her giving you a relation and saying, show show if it is transitive or not, show if it is reflexive or not, show if it is symmetric or not. I want to do, I think 15 next. So let's look at 15. So all right. And in 15, R is, well, actually they use D, so let's just erase that whole top line. They use D to name the relation, and they use D because then the relation we're doing is the divides relation, and it's gonna be on, specifically says it's on z plus, so positive integers. We can't do, we can't do 0 because we can't divide by 0 in this case. Actually, why is she not doing 0? So give me a second. Yeah, she's not doing 0 because there's a specific, so we're gonna do m divides into n, and specifically if you had 0 divides into 0, or 0 divided by 0, we get, that's one of our division results that doesn't work. And you get indeterminate because there's actually an infinite number of answers for that. So that's why she's not including 0 here. So sorry. So D is the divides relation. The domain and codomain is the positive integers. And the divides relation is just the relation version of the divides definition that we've been doing, for a while in this class. So M divides N if and only if M divides N, that it fits that definition. So again, you do a problem like this, you'll see once we get to showing it's reflexive, symmetric, transitive, if any of these are true, then naturally your proof is gonna have to involve the divides, what do you call it, the divides definition. And so I bring that up because in grading some of y'all's homework, I have seen not a ton, not often, but not just a couple times. So what I've seen is that now that we're getting to chapter 6, 7, and 8, when you see some of these old definitions, even odd, divides, etc., I've seen a couple people, like couple times people tend to want to, again, just use some practical arithmetic logic to sort of make sense of the situation, and what do you call it, describe it and prove it that way. But if you're referencing some definition that we've had in this book, you have to prove it using that definition. You cannot prove it using just sort of intuition and practical arithmetic, essentially. So just keep that in mind. So if you see divides, even, odd, rational, etc., that means you have to use that definition to prove things when something is true. So just keep that in mind. So like I said, I'm just only bringing that up because I've seen a tendency for people to be like, okay, I'm done with chapter 4, I'm in chapter 6, I'm in chapter 7, then I can just sort of ad hoc explain it. And unfortunately you can't. You've got to prove things using definitions. So well, okay, I don't think I changed anything there. So let's look at reflexive. Let's determine if this relation is reflexive, symmetric, and transitive. So reflexive means that I look at every element in my domain and I ask myself, does it divide itself? And it see itself in the mirror being the divisibility definition. And what would you guys say there? I'll give you a second on this because I know you guys you didn't look at this for the reading. So what do y'all think? And it seems natural, again, referencing, even if you think about that last example we did in 8.1, I guess, again, sneaky on my part, I set you up with an example at the end of 8.1 that sets you up for a problem we're doing in 8.2. But if you think about that last example, it was about divides. It was just only on certain numbers, 2 through 8, but everything divided itself. Kind of saw that pretty clearly. So this is reflexive, but the difference here is if we're saying, yes, it's reflexive, we got to prove it, which means we need a formal proof, like I said, that involves divisibility definition. Again, in 8.1, it was just certain numbers and we kind of saw it arithmetic wise. But if you're trying to prove for all, you have to write a formal proof for it. All right. So reflexive, yes, which means I've got to write a proof here. So first of all, I'm going to suppose X is in my domain. And once I have this, my goal is I've got to show that this divides itself. So let's remind ourselves of the divisibility definition. What does it mean to be divisible? And again, it doesn't mean maybe what your intuition and practical arithmetic are telling you. It doesn't mean that I can divide one number into another. I mean, that's the action we would take in our heads. But what that means, the definition of divisibility, m divides n, if and only if m times an integer gives me n. So remember, that was our definition. So that's what I got to show here. So x divides x, I can only claim that's true if I can show x times an integer gives me x. But can I do that? Good. For any number, it doesn't matter what number it is, x times 1 is x. And so that's going to be exactly our proof. So suppose x is in z plus. Sorry. Let me change. Yes. Suppose x is in z plus. Now x times 1 equals x. And I know 1 is an integer, so now I have it. This is the divisibility definition. X divides into x if I can show that x times an integer equals x. Therefore, x divides into x. Good. And we've got it. So that would be my proof that the divisibility, this little relation, this little operator is, what do you call it? Is reflexive. All right, so now let's move to symmetric. So for symmetric, what I want to think about is I want to think about one, a first number that divides a second number. So I'm going to set myself up with x is related to y, which in this case means x divides y. And then the question is, so if I have one number that divides another, is it always true that I can flip it around? If x divides y, then does y divide x? And what would you guys say? Good. And so hopefully you're kind of thinking of some numbers in your head. Again, that's not going to give you a proof, but it's going to tell you whether you should go true or false. You're thinking of some numbers in your head, and hopefully you're seeing pretty easily that this doesn't work. So for instance, 3 divides 6, but does 6 divide 3? No. So this is a no. Oh, I don't know why this. Well, okay. Maybe that's why I did this one. No. So we can say 3 divides 6, but 6 does not divide 3. Because you need to multiply it by half, and that's not an integer. But again, the reader can kind of see that. Good. So this is a counterexample, and that's all I need to show that something's false. Right, and then let's try to think through transitive. So transitive, I've got my setup is a degree more complicated. I've got to pick 3 numbers where the first, in this case, so again, retranslating it for our relation, the first divides the second, and then the second divides the third, and then the question is, does the first divide the third? Kind of think through some numbers. Does that seem to be true all the time? It does sort of seem to be true. Again, that intuition is not a proof, but it does lead us to this. It looks like this is true. And so let's get a proof going. So we are going to suppose everything we need for this if part, everything in the if part and everything we need for the if part. So we're going to suppose X comma Y comma Z are positive integers. First of all, so they have to be part of the domain. And yeah, notice the similarity in kind of how I'm writing this out and structure. It's very intentional. It's not that you have to like be copycat like that. But I do want to be, I'm very intentional about writing it out in the same structure because I want you guys to catch sort of the pattern of these proofs for these different properties and what you need for them. So suppose X, Y, and Z are positive integers and X divides Y and Y divides Z. So if this was true, then what I gotta show then is that X divides Z. But again, the big point here is if you're gonna prove that, you gotta prove that using the definition of divisibility. So then this proof from here is gonna be very much like one of the proofs for divisibility that you guys did in 4.4, or just one of those, the whole, any proof that we've done that involves divisibility really throughout this course at this point. All right, so we have our suppose. I have that X divides Y and Y divides Z. So again, like a lot of our direct proofs, once I know this is true, I'm going to expound on that. I'm going to use the definition of divisibility to give me some more details here. So what this means is that X times A, for instance, would equal Y. Y times B maybe equals Z for integers A and B, which they would have to be positive integers in this case, but for our definition, they just have to be integers. And so this is definition of divisibility. Again, hopefully this just kind of starts to ring a bell. Maybe it's a groan or maybe it's a aha, but either way, kind of see these parts. So we're using definition of visibility to give us some more details, some more definition about between X and Y and Z. And you can start to see from here that then we can use some algebra to start to get to where we want to get. What we want to get to is that X divides Z. So in the end, what I need to see is that X times an integer gives me Z. So I want to give you guys a second to see if you can hack together the rest of this proof. And maybe you can, maybe you can't. I think you guys can though. So again, hopefully this rings a lot of bells with every divisibility proof we've seen so far. So from here, you should be able to kind of string together the equations, the algebra that you need to show that X divides Z. So I will pause on my side, pause on your side, see if you can put the rest of this proof together. All right, let's see what y'all came up with here. Or I guess I can't see, but um, so when I'm looking at this, I noticed that, so I want to show eventually that X times an integer is Z. And so one of these equations that I introduced here from the definitions of divisibility has Z in it. So I want to start with that equation, but it also has a Y in it, which I know from the other equation I can replace with XA. So we can do a bit of substitution here. Then Z equals XA times B, substitution. And then I can do some nice algebra I already know. I can make this X times AB. And of course, that means I'm looking a lot closer at my definition. I'm looking like my definition that I want. I want X times an integer is Z. So the biggest thing here is I just need to justify why the AB is an integer. So why is AB an integer? Good. In this case, products of integers. So I also want to bring this up because again, in grading some of y'all's homework the last couple weeks, what do you call it? That's, I think, one of the few, so you guys have done really good actually on a lot of the proofs, but one of the few things that I see not just a couple people, but most people consistently missing is you'll get to some place where, this thing needs to be an integer and you're just like, oh, it's an integer. So you'll literally say in your proof, and that's an integer, so we know that such and such, it's divisible or it's even or it's odd or whatever it was going to be. And so again, just a little bit of relaxation that you guys have had away from what we did in chapter 4 and 5. Um, to prove to the reader that it's an integer, you need to tell me that it's a product of integers. So yes, I see that these are integers and they're multiplied, but I need you then to say that in the proof. That reason has to be in the proof. So you'll notice for some of your proofs, a lot of times your proofs have been really good, mostly correct, and I'll take off either 0.1 or 0.2 if there's some other errors from the full credit in the proof. And like half the time, honestly, it's because you just said it was an integer, but you didn't justify why it's an integer. So AB is an integer because it's a product of integers. But once we have that, then we have it, x divides z. X divides z, and that's what I needed. I started out with x divides y divides z, and I proved that all the time, in every case, that means x divides z. So this is a transitive relation. Notice in 15, we have another relation that is reflexive and transitive, but not symmetric. So if you go back to what we did in 9, the greater than or equal to relation, it was also reflexive, transitive, but not symmetric. So we won't explore as much as I would like to in this class just because we don't have the time, because it's not focused on being a theoretical math class. But still, that should pique your interest a little. So what we're saying basically is the divisibility relation or operator kind of acts, not just kind of, acts exactly like a greater than or equal to comparison or operator. So divisibility has the same patterns as greater than or equal to. So why? That's kind of an interesting thing, because they're really two completely different contexts and things, but they act the same. So why? And if I group these things together, could I come up with some property or group that they fit into of all the relations that have reflexive, transitive, but not symmetric? And what would be true about all of those relations together? Could I find some pattern about all of those relations? So again, if you go on, if that kind of idea interests you, then you want to go on to some higher mathematics. You want to go on some other theoretical proofs-based classes, because that's actually what they do. From here, it's just basically when you get to the next theoretical math class, it's okay, now the relations are objects, and we group them together and we try to figure out what properties all those relations have and why do they relate, why are they the same as each other, etc. So if you like that, it's really cool. If you don't do it. Again, this is for this college, the way this class is taught, not just the way this class is taught, the people that I'm getting for this class are mostly computer science majors. So I just want to give you a peek of that idea, those thoughts and those curiosities. And if that peak is really awesome and enough for you, then you should definitely think about going on to some theoretical math classes, even if it's not a major, just a minor, obviously. Um, and if it's just a curiosity and cool, but it doesn't pique as much interest, then continue doing what you're doing. So, cool. All right. Let's look at one more. So we'll look at 25. So what did I say? 25. In here, so as always, I want to look at relations with different contexts, and as always, I want to look at least one that has a computer science context. So let A be the set of all strings of A's and B's of length 4. So if you remember, actually, we had an example. Give me a second. Was it in? Was it in the last section? It was either in 8.1 or somewhere in chapter 7, but maybe it was 8.1. But we had this exact kind of same, not just same, this exact setup. We're looking at strings of length 4. We're going to define a relation on those strings as follows. For every S, T, and A, S is related to T if they have the same first two characters. So this is that same first two characters. I'm pretty sure this was in 8.1. I kind of like that she actually does this. So you actually see that progressively through a section, she'll actually use the same setup, improve, kind of show different things about it as you get deeper into the section. So very, very smart on her part. So let me kind of reduce that down. So this is a relation R from, so for this, you're just gonna have to know what A means, just by reading the PDF there. But any two strings of length 4 in A, S is related to T, if and only if S and T and T. Space there. Have the same first two characters. So again, I think it was the last section, like we saw in the last section, AABB is going to be related to triple AB because the first two characters are the same. AB is going to be related to A triple B because the first two characters are the same. So let's start with reflexive. So is this relation reflexive? And again, this is a good example too of not only is the context, so the context is something you kind of have to think through. What you could do honestly on this is you could actually write out all of your strings of length 4, which there would be 16 of them. And if you did that, it would be a horribly big one, but you could make a direct graph and start to figure out the relations on these things. So what I'm saying is on this one, kind of like the first one, you could actually visualize all the pieces. But since there's so many pieces, our head actually generally, so for most people's brain, you sort through this faster by just again using this description as a stand-in and just having your head kind of work through the pieces. So for reflexive, we want to check. So I guess I'm saying all that to say I'm not going to write out all the possible strings and relations, the directed graph for this. We're just going to think our way through it. So for reflexive, I want to know is every string, in this case, string in A, string of length 4, is it related to itself? So does every string have the same first two characters as itself? What do you guys think? Good, that's pretty obvious. An object obviously matches itself. And that's essentially going to be our proof. So notice the thing about this proof. This proof is going to be interesting because none of this is algebraic. So we can't use equations and algebraic manipulations like we did on the last one. And we can't even use some sort of base arithmetic knowledge like we did on 9. We just sort of have to basically talk our way through this. Especially on something like this, like I said, it's because strings are not an algebraic entity. They're not a number. They're not something that we could easily relate that way. And we also get to do that because our relation, the essentially the equation for our relation was given as a sentence. So this description, S and T have the same first two characters, becomes a way for us to prove and show to the reader, as long as they can visualize it, that obviously, like, this is true. This is a correct point in the argument. So for instance, on reflexive, yes, again, it's very obvious that string is related to itself. It has the same first two characters. So we're basically going to say that. So we're still going to suppose. So suppose S is in A, then the first two characters of S match the first two characters of S. So like I said, I'm going to say in sentence form, in words, the condition that I need to show the reader, which is exactly the sentence that I have here. First two characters of S match the first two characters of S. And that actually is enough, but you could say here, so, well, I just need a little more room. So, tool. So S is related to S. That would be the reflexive part of the proof. So it is reflexive. Let me give myself a little more room here. So then symmetric. Symmetric, again, what I'm looking for is symmetry. I want to see if one thing is related to another, then that second thing is automatically related to the first, that you can flip it around and the relation still works. So in terms of our context here, I want to think about some string of length 4, and so suppose we have two strings where the first and the second string both have the same first two characters. So S is related to T. Then does it have to be true that T is related to S, that T has the same first two characters as S? And again, not only verbally, but logically, that definitely has to be true. So the interesting thing about this is again, like I was saying, you actually don't have to think through the 16 possible, what do you call it, strings that we're getting out of this. This description is actually enough to prove not only to the reader, but to our own mind that this has to be true. And I don't even need to think about the details. So symmetric then is also going to be true. If S is related to T, the first two characters of S are the first two characters of T, then I can definitely flip it around. I mean, if they match, they match. So we're going to write basically that. We're going to write something like that. So again, I'll pause and you pause. See if you can write this one out. All right, let's see what you came up with. Or again, I'll suppose what you came up with, but let's see what you came up with. So this is definitely symmetric, so we're gonna suppose the first part of this, so suppose, and what am I using? S's and T's, sure. So suppose S comma T are in A, and S is related to T. Good. Now notice kind of like really like not just almost all of our direct proofs. Once I have S is related to T, R has a definition, and that definition is this sentence. So I can then give some detail about S and T using that sentence, and then from there I can sort of make my argument. So suppose S and T are in A, and S is related to T. So the first two characters of S are the same as first two character, well, let me save some real estate here, yeah. As T, we'll just, that's sort of understood, same as T. So then, obviously, so I will say this next line is gonna sound redundant, and I would probably even argue whether you have to even include it. But, so the first two characters of S are the same as T. Then the first two characters of T are the same as S. T are the same as S. So like I said, I would almost argue that you probably don't need to include this line because there's basically some, there's some symmetric property of, languages, not even just the English language, but any language. Where, I mean, I've basically said here that the first two characters of S and T are the same. So that inherently works both ways. We kind of understand that is in terms of language. But to be sure, I'm gonna put this line here. Then the first two characters of T are the same as S. Therefore, T is related to S. And we've got symmetric. Then we would do something very similar for transitive. So my one worry here is we're kind of running out of room for transitive. So let me box this off first. And let's put transitive over here. So in transitive, what I'm doing is I'm thinking of, again, three total strings. The first string has the same two characters as the second string, and the second two has the same two characters as the third. So then the question is, does it then make sense that the first string has the same two characters as the third? And what would you guys say? Good. So again, that actually kind of makes sense. So we're gonna start with our suppose, and we're basically, again, like I said, the point of this is when they give you a definition that's essentially a sentence, that sentence, the observations of that sentence are then your definition, and you're allowed to use that to make your argument. So we're gonna do that same thing here. So suppose, let's see, S, R, and T are in A, and S is related to R is related to T. And because I don't have enough, I'm not gonna have enough room to write this, I'll just sort of orate, so I'll verbalize the argument from here. But again, I actually want to give you a second to sort of form this argument on your own. And I think at this point, not only you probably obviously see it, but you definitely can write this out on your own. I'll pause, you pause, go ahead and see if you can write this argument out. All right. So again, I can't write it up here, but your argument should go roughly like this. So suppose, again, let's pretend that says supposed to. Suppose S, R, and T are an A. S is related to R and R is related to T. Then, since S is related to R, that means or you could just say then, the last two characters of S are the same as the last two characters of R. And the last two characters of R is the same as the last two characters of T. You could say from there, let's see, well, do you need to say, is there a transitive property to language too? Do you need to, give me a second, do we need to say much else? Well, you could just say something like, since the first two characters of S match the first two characters of R, and those first two characters match the first two characters of T, then the first two characters of S must match the first two characters of T. Therefore, S is related to T. You could say something like that, and that would be it. Good. So those are a bunch of relations and proving or disproving if it doesn't work, whether they're reflexive, symmetric, or transitive. So notice this last relation actually had all three properties: reflexive, symmetric, and transitive. So in the next section, we'll look at a lot more relations like that have all three properties because there's something special about them. But we'll see that in the next section. So good stuff. See you guys on the next one.